So let's start off now by thinking about state action value. So imagine we're in current state S, and this has got a value of v pi of S, of course. And then we take a particular action from our policy, and then we think about this particular action state condition that we're in. From that point onwards, then there's going to be a stochastic transition. So given the fact that we're in state S, we take action A, we'll stochastically transition to another state S prime, right? So which will take us to one of many possible states that the transition matrix will actually let us take. So when we actually do this transition from S to S prime, we're going to get an immediate reward R, and we will move also into the resulting state S prime, and this will be associated also with a value. It'll have a value v pi of S prime. So given that we are in state S and we take action A, so we're not thinking this time about all the other possible actions that we could have taken, and we're just thinking about just being in this particular state S and taking an action A, we can define the state action value as being, right, the expected reward we get from being in state S and taking action A, as being the expectation of the gain when we're in state S and take action A. And we're going to write this as a Q value, so we're going to say Q of pi S given A. So this is going to give us the value under the policy for S, for state S, when and we then take action A. So let's look at this then again for a particular action A. Under this particular action A, then we're going to be subjected to a stochastic transition probability S prime given S and A, and this will lead to the transition to a particular state S prime from many others that we could possibly have got to, and this transition will also lead to immediate reward R, and there'll be also reward and value associated with state S prime, which we can then discount with the factor gamma. So let's think about then, we've got this state action pair. When we make the transition from S to S prime, we'll get a total reward of R plus this discounted future reward. So gamma v pi of S prime. And the probability we get this reward is given now just by the transition probability. The policy doesn't come into it because we're already given the A, right? So we're given the A. Now the only thing that affects where we end up is going to be the transition probability. So the probability we get this reward is now P S prime given S and A. So it's just basically the probability distribution over the future states S prime, given the fact that we were in S and we took action A. So given that's the future reward, and given that's the probability, we can, again, using the definition of expectation, we can calculate our expected value of the state action pair, right? And we do that again by summing over all the possible future states S prime, and multiply the future reward with the probability of it occurring. Okay. So we end up with, again, with a simple expression. It's just the probability of it occurring is given by this transition probability. That's this part here. That's the first part down here. The actual value that we're going to get that is the future reward term here. So it's R plus gamma v pi of S prime. And like I said, in order to calculate the expectation, we sum those values up across all the possible future states S prime. And this leads to our Q value, Q of S and A. So expressed more formally then, we'd write the Bellman equation down like this. Let's go through the thing a little bit more rigorously. So we've got our value of state S under policy pi, and we know that that's given by, first of all, summing across all A for the policy pi A given S, multiplied by summing across all of future states S prime of the transition matrix, multiplied by all the rewards. Now, if we define the state action values as being the expected gain given the state and the action, right? So rather than just given the state, it's given the state and the action. This leads to the expression that we've just seen, that we can write the expected state active values is given by the sum across all future states of this transition probability multiplied by the reward term. So you can see that the state values, state action values are basically another average. It's another expectation. And we can also write the value function as well in terms of this Q function. We see that this second part of the Bellman equation here on the right hand side is actually the Q value. So we can substitute in the Q value for this sum across S prime term, and then immediately we have this expression here that the value of state S under pi, policy pi, is just the sum across all actions of pi A given S multiplied by Q of S and A. So let's think about policy iteration. So what is the value of the state under an optimal policy? Let's look at the Bellman equation. And what we can see is, first of all, we notice that this second part on the right hand side is the state action values, the Q value, so Q of S and A. That is explicitly writing it down. We can just rewrite this term here as Q under pi of S and A. Now we can always improve policy by choosing the best action, right? So rather than just using all, so when we're actually looking at this expression here, what we're doing when we're calculating the value, we're actually averaging across all the possible actions that we can take. But in actual fact, we'll get a better value if we just pick the best action, because then we wouldn't have to average it across other ones, which and some of them might have a very bad value. So if we pick the best one, then we'll get the best possible value overall. So what we really care about is picking the best action rather than using a sum across the expectation across all of them. So let's imagine now we're going to choose the best action and evaluate the rest of the expression, which is basically this bit here, which is the Q S of A term. Okay, and that's exactly what we've got here. So we see that the value, the best action, the best value, arises from the best action, which we can then pick from the Q expression. So given that we've got our Q expression, the best action is going to be given by the action which leads to the largest value, right? And the way we can write that mathematically is saying, well, first of all, we've got this Q value, Q S of A, and this actually contains the value, but the best action is going to be the A that gives us the largest value. And the way we actually write that mathematically is rather than just using max, which would return the maximum state action value, we say argmax, so it's the argument of the maximum, and that will then return the actual, if you like, the argument, the action in this case, which gives the maximum to this expression. So putting this expression into our equation, basically what we can see is we can write an expression now for the optimal policy, right, which we're going to call pi prime of S, and that's basically the expression for the Q expression, which gives us the best possible value, but we want the action. So it's going to be the argmax of our sum across all future states S prime, transition matrix multiplied by the reward term. And this is what we call a greedy action selection, because it's picking the biggest in order to get the best possible result. And if we did this and do it iteratively, then we're guaranteed to actually improve policy, because we're picking the best policy each time and then updating for all values of S. So if we do that, we can pick the best optimal policy. So to summarise, the value of a state, or the best value of a state, can be achieved by, it's basically the expected value of gain for state S, taking action T, for the best possible action, right? So putting the equation in for what Q comes out as, Q of A and S, it comes out as being this sum, and in this particular case, let's get rid of that form, because we're going to marginalise over R. We always look at this expression because it's a bit simpler. So what this is saying is this is the expression for Q, which is the probability transition matrix multiplied by the reward, which is then summed across all future states S prime, and it's the particular max action that we want to give us the max value of this expression. And this is obviously greedy action selection. And if we want to pick the optimal policy, so the best policy, we can actually do that by picking the action that generates this maximum value, and then we update the policy with that particular action, so we can update what we have for that. So we can now show that we've shown that you can use dynamic program to compute optimal policies. So what we can actually do now is alternate between policy evaluation and policy improvement, right? And if we do that, first of all we evaluate the policy, and then in order to get our value function, and then we can improve policy in order to get a better policy. So we can use this iteratively to first of all estimate what we have for the value function, and then also to improve what we have for policy by doing one thing after another. So we have this policy evaluation stage where we say that we're going to update the value just using the Bellman equation, right? So we just evaluate across all possible, summing across all possible actions of the policy multiplied by the sum across all possible future states of the transition matrix multiplied by the reward. And then we update all the policies by choosing from our Q function, which is what this is here. We choose the action that gives the biggest value, and then we use that to update the policy with until it converges. And basically the idea of just doing a value, well, there's two parts to that, as you saw in the other diagram, but this is really a circular thing, so it goes round and round iteratively. We estimate the value using the particular policy we have at any particular time, and then we improve the policy using this greedy policy improvement scheme, and we can keep going round and round and round iteratively. We do one and then the other, then one and then the other, and then basically we end up with hopefully the optimal policy. And the idea is we start off somewhere in value space and policy space, which is a little bit off, and then we basically iterate towards what is hopefully the optimal value function and the optimal policy that we have. And this is just Sutton and Bartow's pseudo-code for it. I shan't go through it into too much detail, but basically here's the policy evaluation loop. So the important thing to note, for each S, for each state, what we're doing here is we're just noticing what value we had to start with, and then we're doing the policy update here, right? This is the evaluating the policy, so we're just applying the Bellman equation here in order to update the value. And then what we do is, after that, we do a policy improvement down here in order to pick the best, if you like, the best action to give us the largest value, but we actually then use that to actually update the policy. We can also do value iteration. So policy iteration we just did involved evaluating policy at every step, but if we want we could just look at the value instead, and this finds optimal policy is again, it's a greedy method using a simple backup. So what we do this time is, rather than calculating the value by summing across all possible, looking at the sum across all actions of the policy, what we do is we just choose the action which gives the best value, right? So we just use choose the best action and do update in that way. And here is the basically the Sutton and Bartow code for it. The important thing to notice is what we're doing is, when we're updating the value function, what we're doing, again, we're using this argmax notation. So we're picking the best action out of here in order to actually do this process. Just one last thing, there's two ways you can actually update these things when you're doing it. You can either do things using two copies of value, for example. If when you're updating value, you could be processing on the old one, right, and then updating a new version, right, and right at the end you then update the whole, you switch the two over, or you basically then you use the values again, right? You update the values with the new values. Or you can do things online, so you're actually, rather than effectively working with the last copy, and when you're getting data out, what you can do is you can just have a single copy of the value functions, and you're continuously updating them as you go along.